Hello everybody and welcome to DirectX 11 tutorial 32. In this tutorial we are going to first go over how we would mathematically calculate our pitch and our yaw if we wanted to actually have the camera look at a certain position. And then we are also going to go over implementing it. So I'm going to have timestamps on the description, and they should be on the screen right now, showing what time to skip to for each thing. So if you already know how you would do it mathematically and you're just going to skip to the programming part, you can do that. Or if you want to follow along, you can do that as well. So the first thing we're going to cover is something called the arctangent, or the inverse of tangent. So you might see this written like this, and you might also see it written like that. For this, I'm just going to write it as a tan, because in C++, this is the function that we are going to be calling. So what is a tan, and what are we using it for? Well, let's say that we have a triangle. More specifically, let's say that we have a 90-degree triangle. So in a 90-degree triangle, there is a perfect right angle, and then we have two other angles. Well, if we have, let's say, 3 on this side and 4 on this side, and we want to determine this angle, we can use arctangent to determine what this angle is. So the way that it works is we will do the arctangent, and we will pass in the far value divided by the adjacent value. Usually when they teach it, they say opposite over adjacent, but I just like to think far because this actual line is far away from the angle, while the 3 is actually adjacent. So what we would do, switch to another color, get some color going. We would do the arctangent. We would say, okay, 4 over 3. And what we would get for this would be 0.92 radians. Now, 0.92 radians, we can take 0.92 and multiply that by 360 and divide it by 2 pi to convert it to degrees, and we would get about 53 degrees. So we now know that this is 53 degrees. And let's say that we wanted to calculate this angle up here. We want to calculate theta. That's what that symbol is. That 0 with the line through it, that is theta. So what we will do is we will say, okay, arctangent. In this case, the far away side length is 3. And the adjacent side length is 4. So we put 3 over 4. And for this, we would get 0.64 radians. And we'd do the same conversion that we did before, and we would get about 37 degrees. So this makes sense, because you know that for a triangle, all of the degrees have to add up to 180. We get 90 from the first right angle right there. And then we got 53 plus 37. And this adds up to 180 degrees. So now we know how to use arctangent, but how will we calculate the pitch and the yaw for the camera? Well, first let's take a look at calculating the pitch. So we have our graph, and in this example we're going to look at the x and y axis initially. Now let's say that our camera is over here, and we want to determine the angle that we would need to look at the very origin. So we are looking for this angle right here. Well, let's say that we know that this length right here is 8, and that this length is 2. What we could do is we could say the arctangent and we could pass in the far value, which is 2, over the near value, or the adjacent value, which is 8. And what this would get us is 0.245 radians. So if we turn our camera down 0.245 radians, then we will be looking at the origin of this graph. Now let's do another example. Let's say that our eye is down here this time, or our camera rather, and we want to look up at the center. It's not the best triangle, but work with me here. So now we are calculating this angle. Well, let's say that this length right here is 8, and this length right here is 2. We could do the arctangent. We could pass in 2 over 8. And once again, we would get the same 0.245 radians. Now, the thing about this is, yeah, we do need to adjust 0.245 radians, but these aren't the same, you know. In this example, the top one, we are turning down. In the bottom example, we need to turn up to look at the center. So what we actually need to take into account is this y value a negative or a positive? So in the bottom example, it's actually a negative 2. So we would be taking the arctangent of negative 2 over 8. So we would adjust by negative 0.245 radians in this bottom example. Now, you might be wondering, well, what if we had something in the bottom left quadrant, right? Because in that situation, our x value would be negative, and our y value would also be negative, so it would give us the wrong angle. However, what is actually going to happen is we are not only going to be looking at the x-axis, we are also having to take into account the z-axis. Now I have this example, which this isn't going to be for download, but just to demonstrate in the video. So I have it set up where my camera will focus in on the origin. And you see currently I'm moving up and down the z-axis. And when I get closer, I'm looking down at a steeper angle. And when I get further away, it's not as steep of an angle. Now, what is important to note is that the z-axis affects this. However, the x-axis will also affect it. So let's take a look at that. Now, it's kind of hard to see because the object is completely flat down the origin, but you can see we're looking down more as we get closer to the center, and then when we move away, we are looking up more. So what's important to take from this is that we will be taking into account both our x distance and our z distance from the point that we are trying to look at. Now, the reason that this is important is because we won't actually have to worry about negative x values and negative z values. And the reason is because in order to get the actual distance with our x and z values, we will use the distance formula. And the distance formula is the square root of x times x plus z times z. And we know that when you multiply a negative number by itself, you get a positive number. So this will always give us back a positive number. With what we currently know, we should be able to implement the pitch adjustment. So back in our camera header, let's add a new function. In this new function, we're just going to call it setLookAtPos, and you know it's just setting the position you're looking at, and it will take in a position to look at. Let's go to create the definition. So first, let's make sure that the position we're looking at is not the same as our current position, because If it is, then we don't need to update the camera because there's no way for us to look at exactly where we are at. If the positions do match, we'll just return and not do anything. However, if they don't match, we need to figure out the difference in these positions. So we're going to take our position and subtract the lookat position to get the vector from our position to the lookat position. Next, we are going to initialize our pitch to 0, and we are going to check as long as the position that we need to look at is not at the same y value, so as long as we actually have to change the pitch from 0, then we're going to calculate the distance by just using the distance formula. And then we are going to call arctangent, and we're going to pass in our y value, which would be the far value, divided by our distance. The last thing we need to do is we need to just set our rotation, and for our pitch, we'll pass in the pitch, and then for our yaw and roll, we'll currently pass in 0. So let's test this out. Let's go to the graphics CPP, and up here, after we adjust our position, let's set our lookat position to be the center, and our camera should now, I just have to change these arguments to be a xmfloat3. Alright, now let's test this out, and what should happen is as our camera raises, it's looking down at that object. So now we are successfully adjusting our pitch. So next what we have to do is determine how are we going to calculate the yaw. Now let's take a look at how yaw works. I'm currently locked in on the center of the screen with this demo. And you see the yaw is turning as my x value and z values change as I go around. However, what about my y value? What if I go up and down? Now if you notice, the yaw is actually not modified at all by this. All that we are seeing is the effect of the pitch changing. So what we know is that when we calculate the yaw, all that we have to take into account is the x value as well as the z value. So now we are going to take a look at how we would mathematically determine the yaw. And keep in mind, we are looking down from a bird's eye view. That is the positive z, negative x, and positive x directions. So let's start with something from this quadrant. So we know that initially our eye is looking straight up, or rather we are looking in the positive z direction. We're not looking up. So just think of this as we're looking towards the positive z direction. So we need to determine if we had a triangle like this, we are looking for this angle right here, that theta. Well, let's say that we had a 4 right here, which we know this would really be negative 4, because this is z from negative 4 to 0. And let's say that this value up here was 6 for our x. What we could do, so we could say the arctangent of 6 over negative 4 is equal to negative 0.98 radians. And this is how many radians we need to turn in order to be looking at the center. Alternatively, let's say that we started over here in the bottom left. So we have our eye looking up, and let's say that this is 4, but we show it as negative 4 because it's on the negative quadrant for z, and our x in this case would be negative 6. Well, we could say the arctangent of negative 6 over negative 4, and what we would get is just positive 0.9 radians. So it's we're turning the opposite direction, but we still need to turn the same amount to get to the origin. It's just in the other direction. However, where it becomes a little bit tricky is what if we started up here? Because you see, in this situation, we might actually have to turn more than 180 degrees. And arctangent, when we are using it, we should only be getting something really between 0 and 90 degrees, because we have a right triangle, and triangles can only have 180 degrees. Well, what we will do is, first we know that we have to completely flip the direction that the eye is facing. So first, we will rotate it by pi over 2. And what that will do is now our eye will be looking down, and then we can create our triangle, and we can say, alright, let's say that we have 3 for the side close to us, 4 for the far away side. We could say the arctangent of 4 over 3 is equal to 0.92 radians. And then we could say, okay, well, let's add I just realized I put pi over 2. I meant to just put pi. Ignore that over 2. It's just supposed to be pi, which is 3.14, etc. So we would add pi, because we want to turn 180 degrees. So we would say 3.14, which is pi, plus 0.92, and we would get that we have to move by about 4.07 radians. And we could do the same example on this side. I'm not going to. And then we would just add pi after we do the calculation for the triangle. So now let's look into implementing the yaw. So back in our set LookAtPos, after we determine the pitch, we need to determine the yaw. What we will do is, as long as the LookAtPos x value is not 0, because we don't want to get stuck doing something like 0 divided by 0, then what we are going to do is we're going to call the arctangent. And regardless of what x is, if our z is greater than 0, we are going to add that pi to flip the eye around. Now down here in our set rotation, let's add the yaw. And we are not going to concern ourselves with the roll, because that doesn't apply to this. We just want to turn the camera to something. We're not trying to, turn the camera like an airplane doing a barrel roll or something. So up in our graphics CPP, in our render frame, let's change how we're moving the camera to check the yaw. So instead of moving up, we're going to move it to the right. So let's test this out and see what we get. Alright, and we are moving to the right, and you see our camera is turning to the left to keep staring at that object. And as it gets further away, the object's going to get flatter, and it's going to become more impossible to see since it's completely flat. And that is properly put in. So now we are able to tell our camera to look at a specific position, but we also have all of this other functionality. So the set look at position, that's not really something that we really needed, at least not currently, but it will be nice in the future if you ever want to just, hey, put your camera somewhere and have it looking directly at a position and not do all these calculations and have them memorized. So that is all that we are going to cover for right now. In the next tutorial, we are going to look at how we can move the camera around. Not like this, but with actually using, WASD and using the mouse to turn the camera and things like that.